In this lesson, we're going to talk about color blending. So color blending is essentially this equation. All of the color blending that we've done so far has been done inside of a single shader. Anytime we've used mix or that smooth step when we're doing interpolation between two colors inside of a shader, what we're doing is blending. But the blending that I'm talking about now is blending between pixels that have already been written to the frame buffer. So now we're building a source color. That's the pixel that we're actively working on, the fragment that we're intending to write. And then there's a destination color. The destination color refers to the pixel that is already at that position in the frame buffer. Now, how can this happen, or why would we do this? Well, we're going to use transparency as our example. And imagine how transparency works, right? Transparency works where we have translucent objects that are in front of objects that are either also transparent or translucent or opaque. The color of the transparent object is a function of whatever's behind it. So that's what I'm talking about when I talk about color blending. It doesn't just apply to transparency. It can apply to lots of different types of color blending. We're going to focus on transparency here, but the generic operation is source, the source color, times a source blend factor, and then a blend operation. And that blender operation is typically plus, but it can be a variety of things, but plus is what we're going to use. And then destination times a destination factor. And there's lots of source blend factors and destination blend factors. Let's look at the one for transparency. So we'll hop into Visual Studio and let's pull up our transparency mapping fragment shader. Let's look at the vertex shader first. This is the exact same vertex shader that we just did with fogs. There's no difference at all. It's the fragment shader that I care about right now. The fragment shader here, I want to mention that the color sampling doesn't have anything really to do with what we do in the shader. As long as the shader is producing some form of output, then so be it. We can blend it with whatever's already been written to the frame buffer. But in this particular case, I'm going to add a little twist where the alpha channel is not coming from the color texture sampler. In this example, I'm going to have the alpha come from an alpha map or a transparency map. So we're going to specify an alpha map sampler to read from a completely different texture, could be a completely different texture, and just yield its alpha channel. So notice what I'm doing here. This is the same fog shader that we had before. In fact, I'll pull it up and you can see the differences between the two. So here's the fragment shader for the fog demo. Here's the fragment shader for the transparency mapping demo. And they're very, very similar. If you toggle back and forth, you can see the differences there are minor. Now, what I'm doing then in the transparency mapping demo is first sampling an alpha value from this separate texture. I'm going to show you an example of a couple of those textures. So here's an alpha map that is opaque at the bottom. So this is the value 1. So the value 1 for transparency means opaque. And as I get closer to the value 0, you can see that even in the Windows Photo Viewer, this is getting more and more transparent because this is a PNG file that supports transparency. And indeed, the Windows Photo Viewer is showing that. If this wasn't showing transparency, this would look like white to black. This would transition from the color white to the color black because the value here would be closer to 0. Similarly, we can look at this one, which is the shape of a leaf, a maple leaf, and everywhere that's white is opaque. All right, everywhere that's white, the value is not going to be transparent. It's going to be an opaque value. Then all of the stuff that's around it, imagine this is still a rectangular texture, but everything that's around it is going to be transparent. And you'll see how we apply those in just a second. So those are examples of the transparency maps that we're going to be reading from in our alpha map sampler. Now, I'm going to use that sampled alpha in replace of the color texture alpha. So notice that if my fog amount is 1, I'm going to immediately return fog color and then whatever its alpha value would be. So I'm going to alpha it out. And again, instead of using color.a is equal to the sampled color.a, I'm going to use a is equal to the sampled alpha. Now, the other reason I'm doing this, besides just to spice up the demo a little bit, is that I'm already overloading the alpha channel for the color map with the specular map. So I can't have it be both a specular map and an opacity. So that's why we're doing this as a separate texture. So let's look at the demo code. The transparency mapping demo. It's now referencing a transparency mapping effect, which is going to map to those shaders that we just looked at. And we've got all of the values that we had for fog. This is the same sort of stuff that we had for fog. But now we have an alpha map and a trilinear sampler. And we're going to supply that trilinear sampler for both the color texture and the alpha map a bit different here. Let's look at the implementation here. So the transparency mapping demo implementation says, let's build a quad. This is the same quad that we've been using here throughout these demos. Build a vertex buffer from that quad, an index buffer for the quad, load the checkerboard texture, And now we're going to load an alpha map. In this, we're going to use that gradient alpha map that goes from white to black, from opaque to transparent. And I've commented one out for that leaf alpha, and I'm going to uncomment that here in a second, and we'll toggle between the two. And now we're going to create a trilinear sampler. So we're going to GL sample one sampler. This is for our trilinear sampler object that we're storing in as a class member. The min and mag filters, we're going to do trilinear sampling, and we'll do repeat the vertex texture coordinates go out of the range 0 to 1. All of this should be very familiar code. We're going to scale the world matrix. We're going to scale these vertices by a factor of 5. I can make it a big quad. And I'm not doing anything special here for the update, still updating the ambient light and directional light and specular light. What I'm doing differently now is inside of the draw. All of this is the same. Now I'm actually binding the same sampler to both of those indices. That's the first thing that I want to point out. And no problem, we can absolutely do that. The fragment shader says, hey, I've got two different samplers, and I'm going to sample from them differently, but clearly I can pass in the same parameters between the two and then say, all right, for both samplers, use the very same sampler object, no problem. But now I'm going to map to the GL texture 0 slot. So I'm going to GL active texture to the GL texture 0 slot, the color texture, and then another 2D texture for the alpha map for GL texture 1. So that's the difference, right? Is that now I'm going to use two different textures, one for the color texture and one for the alpha map, using those two slots. The other big difference here are these few calls, right? We're going to say GL enable, GL blend. And this is how we enable blending in OpenGL. So GL enable and then GL disable when we're done. We don't want to keep alpha blending turned on or color blending turned on outside of this demo because we want to kind of be good citizens to other components that are rendering. So we're going to undo that state when we're done with it. The next call is GL blend func, and that goes back to that equation that I showed you just a few minutes ago. We're specifying for our GL source alpha and then GL1 minus source alpha for the source and the destination blend function. We're specifying source alpha and inverse source alpha, 1 minus the source alpha. Now, if you think about how that works, that's a slider. That alpha channel is now a slider. If it's 0, then it's entirely transparent. If the alpha is 0, then source times 0 yields 0 plus, that's the default blend operation, plus destination times 1 minus 0, which is 1. All of the color is going to come from what's already in the frame buffer. Conversely, if the source blend factor was 1, then all of the color would come from the source value. If it's 0.5, then half of the color is going to come from the source and half of the color is going to come from the destination. And that's what we're specifying when we say GL source alpha and then GL1 minus source alpha with the GL blend func. I also want to mention that this applies to the alpha as well. So not only to the color channel, but the alpha channel. And there is a way for us to separate those out. I can call GL blend func separate. There's two different functions there that allow me to treat just the alpha channel of the source and destination differently than the color. Here I'm not separating those two out. I'm just saying this is the one blend function that I want. GL source alpha, GL1 minus source alpha, and blend in that fashion. And then we're going to draw as normal in between that enable and disable. Let's see what we get. Okay, so there's our quad. There's the checkerboard map that's applied to it. The alpha channel comes from that gradient value that goes from opaque here and transparent here. This is still lit. This is a lit object. If I move the directional light around, you can see that it's being lit. And if I change the texture map, let's go to that leaf. This is a maple leaf. And the same idea here where we've got everything where it's 1. And here I'm not using a gradient at all, but anywhere that's 1, I'm showing the leaf. Clearly, this is still a quad. It's the same quad that we had just seen. All the rest of those values that are here are invisible. And that is transparency. We can apply these same concepts to any of the lighting models that we've discussed so far. There is one other piece that I want to mention, and that is that order is necessary. We need to concern ourselves with the order in which we draw things. There is the notion of algorithms that make order independent transparency, but I want to note that the alpha objects are typically sorted from back to front. You need to render the stuff behind first. So typically the way that you would render is you would render all of your opaque objects, and it doesn't matter what order you render them in, but it's best to render them from front to back. That sorting is costly, so sometimes people will skip the sorting of front to back for opaque objects. It truly doesn't matter because the Z-buffer will call those out. But to actually make it really efficient so that you don't have what's called pixel overdraw, you can render from front to back for opaque objects. When I say front to back, That's objects that are near the camera, that's the front, and I rendered those first for opaque objects. And if I do that, that same pixel was to be rendered for objects that would otherwise be occluded by the pixel that was drawn first. They won't be passed all the way through the pipeline. They're going to be called out through depth testing. Now conversely, we need to sort from back to front in order for transparent objects. And that makes sense because with transparent objects, since the color of the object is dependent on what's behind it, what's already been in the frame buffer, well then clearly we need to modify what's in the frame buffer first before we write the transparent objects. So that's it for color blending. Next up, we're going to talk about normal mapping.